So now it's, I suppose, my turn to tell you a little bit about what we've been doing. So I'm going to focus a bit on some of the recent work we've been doing on fluorescence, volumetric fluorescence imaging, applying holographic processing to fluorescent signals. But sort of along the way, we'll do a bit of a tour of some of our other modulation-based imaging platforms. So just to motivate this a little bit, as compared to more traditional imaging techniques like laser scanning, where you just take a single focal volume and scan it over in X and Y over top of your sample, and you build up these slices. And then you can assemble those slices into three-dimensional information, and you can get, you know, beautiful images, and you can use myriad contrasts. And but the problem is that building up images slice by slice in this manner is quite slow. And so what we want to do is maintain high resolution, this nice axial information, and the ability to use different contrast mechanisms, but do so very, very quickly. So moving away from scanning towards wide field techniques, such as this is some work we did on second harmonic holography. And so in this work, we illuminate the sample with a pulsed laser beam. The sample generates second harmonic light, which we interfere with a previously generated second harmonic reference beam. And we can record XY spatial information using a camera, and then the hologram, these fringes, encode in them the differential distance that the light traveled between the object generating the second harmonic and the camera. And so then we can, from the hologram, reconstruct the image information along different Z planes, so we can get full volumetric images using holography that look quite comparable to those using laser scanning, but we can do so very quickly because it only requires taking a single two-dimensional picture. And so in this work, we demonstrated image acquisitions of up to 1,500 frames per second in this. This is some mouse skeletal muscle. And the image volume here is about 100 microns on a side. And this works very, very well for this type of contrast. This is second harmonic, which is a coherent process. The problem, here's a little movie of refocusing that collected hologram to different planes, and then you can combine that planar information into an isosurface like you see at the right. And you can get this nice idea of the structure of that muscle. You can only do that if you have a coherent source, which eliminates the ability to use fluorescence. And as fluorescence is pretty widely applied in biological imaging, it's something that that we work with a lot in our lab. We'd like to be able to do this type of holographic processing, but without the requirement of coherent light emission. So the other issue that holography has relative to laser scanning or some other techniques is being a wide field technique, it's quite susceptible to scattering. So that's demonstrated down below. We've taken that same piece of muscle tissue and imaged from different depths. So this first slice is right on the top surface. So we have negligible scattering. And then as we go in 100 microns and then 150 microns, you can see by 150 microns we've got significant degradation of the image quality due to scattering in that tissue. So we'd like both to not require coherence and have something that has a little bit better immunity to the type of scattering that you might see deep in biological samples. So what we ended up doing is we now illuminate the sample with two beams that cross at some angle, and inside of the overlap volume of those beams, it sets up this fringe pattern. So we're projecting a spatial frequency inside of a specimen. And then over the course of a scan, we'll move this beam relative to the other, so we'll change the angle, and that changes the spatial frequency that we're projecting into the sample. And we can collect all of that information on a single element detector. And so this is shown here along the beam propagation direction. We'll call this dimension Z. And then to look a little more closely at how this works, let's consider just a line in X, which is where we sort of got started with doing these modulations. So if we just consider a one-dimensional laser beam, which we apply a temporally dependent modulation to, so different points across the spatial extent of this laser beam get modulated at different temporal frequencies. Then if we use that beam to illuminate an object, here we have a transmissive object, so it attenuates certain parts of the beam and thus attenuates certain frequency components in the electronic spectrum. Collecting the whole beam on a single element detector like a photodiode or a PMT integrates over all of those frequencies, and then in the Fourier domain, the frequency spectrum of the signal coming from that photodiode, we have faithfully reproduced the object transmission function owing to this temporal position-dependent temporal modulation. And so we have dubbed this technique spatially integrated frequency modulated imaging, or SPIFI. The way we apply these modulations is we have a mask that looks like this. This is just a cosine in r and theta. And so spinning this at a constant angular velocity, you can see different points along this illumination beam get these different temporal modulations. So if we focus our laser beam to a line focus, modulate, and then image that line into the object, in this case we have an object that is just a pinhole, and we can translate the pinhole across the object plane, and we get this nice linear mapping between relative position and electronic frequency, all encoded onto this single element detector signal. So as you all seem to be quite a spatial frequency interested group, this type of modulation is equivalently seen as just a swept spatial frequency. So this cosine modulator actually just projects gratings of different periods onto the object and measures the integrated transmission or fluorescence emission. And so what we're really doing here is just making a temporally encoded spatial frequency transform of that object information, such that when we have a temporal signal that looks like up top, and so each point along this trace corresponds to a different spatial frequency, and this is just the illumination laser beam. There's no object in this case. And so if we take this spatial frequency transform that is now encoded in time, Fourier transform it into electronic frequency, we're effectively doing inverse spatial transform, and so electronic frequency here maps directly to location in the lab frame. And so we recover the beam profile. We can use this for imaging. So here is some fluorescent ink just stamped onto a microscope slide, and we measure simultaneously the absorption of light into the fluorescent dye and the fluorescence emission from the sample. And so long as the lifetime of the fluorophore is short compared to the time scale of the modulations, then the fluorescence emission just faithfully follows the applied modulation, and you can do this in fluorescence. And so here we have scanned a stage to get the vertical dimension. This is still just a line imaging technique. And so it works. This is linear fluorescence. It also works with two-photon fluorescence. This is some onion skin dyed with rhodamine that was illuminated by a Ti-sapphire laser. And again, scanned vertically to get that additional sample information. And now that we've encoded spatial information into this electronic frequency, we also looked at other quantities that we could encode in this way. And so using a grating and a curved optic in a Martinez configuration, we took the spectrum of a laser beam and spatially dispersed it across the face of the modulator. So now we've converted wavelength information to spatial information, and then we can use this modulation imaging system to convert that spatial information ultimately into electronic frequency. And we can make a hyperspectral imaging source, or in the very simplest case where you just collect the modulated beam, we've created a spectrometer. And so this is just some test data taken on a Ti-sapphire oscillator, where the solid lines are this modulated single pixel spectrometer measurement, and the dashed lines are a commercial grading spectrometer. You can see pretty good agreement on the right-hand side here. This is very initial data because I didn't have the whole spectrum on the mask, so we lost some light there. But when we put some transmission filters here at 790 and at 830 into the beam, you could recover the filter's transmission function from this hyperspectral information. So that's all encoding information in a single spatial dimension. Sorry, we're having a bit of a... Just hang with me for one moment. Sorry about this. So that was encoding information in a single spatial dimension. So the logical next step for us was to try and encode two-dimensional information without sample scanning, because the sample scanning still works against our desire for rapid multidimensional imaging. So the simple next step was to take a line camera. So here we basically just multiplexed our single pixel arrays into a vertical line. We'll modulate across a horizontal dimension and simultaneously collect about 1,000 of these X images to do two-dimensional imaging. And here I show you this also because when we originally did this work, we had a bit of trouble collecting properly all of the light onto the camera. And so the solution there was to take a linear diffuser and spread the light broadly and just mix up all the light coming from the collection lens and illuminate the camera. And that highlights one of the features of this imaging system, is that since the spatial position is encoded at the object plane by this modulation, it does not matter what path the light takes from the object to the detector. We can, collect, whatever portion of it. As long as we get a representative sample, it doesn't matter what kind of losses we have. It doesn't matter if we purposefully throw away a huge portion of the light. And so this technique did introduce a bit of an artifact here. The linear diffuser is not perfect, and it caused this vertical striping due to the introduced additional speckle. And so by taking some averaging and exploiting the speckle statistics, we can smooth that out within a few shots of this camera. But we still really wanted to get away from cameras entirely to be able to exploit the highest speed operation possible. So we turned to another method of multiplexing, lateral tomography. So in this case, we have the same X-dependent modulation, but now instead of imaging the line to the object, we expand it to a full around beam. But you can see it's still only modulated in one dimension. And so now we rotate the sample within the modulated beam, collect again on a single element detector, and then using standard tomographic reconstruction algorithms, we can acquire X, Y dependent images from this single pixel detector by rotating and measuring these different lateral projections. And you can see here, this is some lines from an Air Force test target illuminated by a beam, and here we've taken a transmission image and not compensated for that beam, so you can see the outline of the beam profile in the recovered data. This turns our problem into a rotational sample scanning problem. So we finally arrived at the free from scanning version of all of this, where we take our X-dependent information and encode it in a small portion of our electronic frequency spectrum, and then we multiplex different X line images from different Y locations at different regions of the electronic spectrum. So here we've shown a cartoon with just 4 Y bins and their corresponding X lineouts. So one other thing to note here is that because of the nature of the Fourier transform and the nature of the illumination system, we actually get 2 copies of each image, one created from the first harmonic of the grading and one created from the negative first, and they're mirrored relative to one another. And so in the multiplex XY image, we have 4 copies of every line image, both plus minus on the Y pixel and then plus minus to that whole sideband on the across the X information, such that when we image a two-dimensional target, like this is the number 6 off of an Air Force test target, we can recover all 4 of those images. But of course, they contain degenerate information. And so the way this multiplexing happens is that we enforce a relatively high differential in the spin rate between those two disks. So one disk spins quite slowly to pack all of the frequency content in a narrow band, and the other one spins very, very quickly to spread out those Y pixel informations in that Fourier spectrum such that we avoid any overlap. And so that's a bit of a limiting factor for that type of imaging. So then we said, what happens if we avoid spinning disks altogether and go directly to DMD? So a DMD is just a large array of mirrors which can be switched on or off quite rapidly. And so we have each of these mirrors in the DMD array is being blinked on and off at a different frequency. And so the spatial information from a certain point is written directly into the amplitude of a different frequency in the electronic spectrum. And so you have however many frequencies you can capture and however many pixels you have limits your image formation. The unfortunate aspect of this type of image formation is while the DMD has a relatively high frame rate of 20 kilohertz, because we need to wait a long enough time to be able to separate out each of those different frequency components, we need a very large number of images, and so the DMD can only hold 40,000 images, and thus can only run for about 2 seconds without being stopped and restarted. And so it really puts a hard limit on the number of pixels you have. Nevertheless, we've binned our DMD pixels into superpixels. Shown here is actually only 32 by 32 because I didn't want to wait 2 seconds, but we can go up to 120 on a side. And this is imaging Air Force test patterns using the same type of modulations as we've seen before to do XY planar imaging. So that only gets us to 2 dimensions. So to explore the 3rd dimension, it's helpful to jump back for a minute. We're going to go back to disks for reasons of convenience. And look, when I talked about those real and conjugate images in the Fourier plane and those being generated by the positive and negative grading orders, so you can sort of see how that works here. As we rotate the disk, you have these 2 beams. You have the undiffracted light, which stays always in the middle, and then these 2 beams sort of breathe relative to that center and scan back and forth across, and it's that differential crossing angle that gives you these spatial frequency projections. If we look at what the modulation pattern looks like, so here the green line is in focus. As we move away from the focal plane in Z, we can see that the gratings get re-imaged and phase conjugate re-imaged as you move away, and that behavior, which is called the Talbot effect, is symmetric in Z. So we don't get any Z-dependent information if we have these 2 sidebands because of this periodic interference structure. If we block one of those orders from the grating, so now that we only have one beam sweeping relative to DC, then we can remove this axial ambiguity, and we get this nice pattern that changes not only along the Z dimension, but also along not only along X, but also along Z, such that each point in XZ sees a unique modulation pattern. I have a little movie here, which hopefully won't crash everything once again. And so the blue dot will move relative to the green. So moving along the focal plane, we saw it just changes the base frequency. And then as it moves in Z, you can see that chirp rate sweeps across. So the slope of the instantaneous frequency gives us Z-dependent information. And the average frequency gives us X-dependent information. And this turns out to be directly analogous to holography, where we've encoded the differential optical path length as a function of time. And so when we're on axis here in Z, we get a nice straight line. The straight differential optical path gives rise to a constant frequency. When we have something that's displaced in Z, and these have different displacements in X as well, you can see we have this curvature here. And that curvature gives rise to a linear chirp in this illumination frequency for those different XZ positions that we can use to locate them. So to demonstrate this capability, we took a single fluorescent bead. I took an X image of it, and then we translated it along Z to map out the whole XZ in amplitude and phase information. And then from a single line out, noted here with the black line, we took that trace, and we took its phase, and for now propagated it forward and backward like you would do in holography, and that's our reconstruction here. And so from this point, we synthesized the rest of the trace data, which is in relatively good agreement with the measured data. And we also, of course, tried it without applying the phase, in which case you get a wildly different reconstruction that doesn't agree with your experiment at all. So we were able to do this while maintaining a diffraction limited resolution, 1 micron, with this objective. And we can do this at 400 planes per second, and we can do it in transmission or with epi-fluorescence collection. So we're able to do, this was taken in epi, we're able to measure the epi-dependent holograms. So here are 2 layers of beads that we can numerically refocus. There's some small beads, and you can see the larger beads going out of focus. Again, these are separated by about 1 millimeter in Z space. So, and this is sample scanned again in the Y dimension because we don't have the full 3D volumetric system up and running yet. But you can see from the yellow arrows indicate 2 different fibers. This is cotton fiber stained with a fluorescent dye. And we can numerically refocus either of these 2 fibers, but of course we have this out of focus fiber is still very clearly visible, which shows that while we have some axial information, we don't have any actual axial sectioning. We don't have Z resolution. And that's highlighted for us once again in this comparison of our chirp fluorescent image system. So this is linear fluorescence of a mouse brain, and as compared to a 2-photon laser scanning. So this was illuminated with a CW 532 nanometer laser. This was illuminated with a 1 micron laser and done 2-photon excitation fluorescence scanning. And you can see the features highlighted in yellow and in blue that appear in this chirped image are from different planes. If you look in the 2-photon image, they're absent in each other's planes. So to get this images to look similar, we have to average over a large number of slices because the optical sectioning capabilities of 2-photon are quite good. So to highlight this problem and look a bit at how we're going to seek to solve it, we'll consider just a disk object. And so the Fourier transform, or the K-space representation of this disk is broad in X and Z spatial frequencies, whereas this line out, which is what we're actually measuring with this imaging system, is broad in X, but it's not particularly broad in Z. And so when we reconstruct something that is short in Z, we get something that looks very beam-like, right? The X dimension agrees quite well, but the Z dimension shows significant variance. So to solve this problem, we're going to turn back to tomography. By rotating the sample, we can project different lineouts across this K-space and fill this in, so measuring rotations, and we can get back to full isotropic resolution. So here is a comparison of a single lineout of an array of beads. This is a simulation, and you can see that everything gets blurred together, and you don't derive any usable information. Whereas if you rotate around a full dimension, you can get back to this nice isotropic resolution. So returning to the ink-stained fibers, we can see that we've done the same thing experimentally, where we took a number of projections as we rotated these fibers around, and we have excellent sectioning in X and Z in this case. So we can do some optically sectioned. We have to scan a little bit. Fluorescence, holographic-like imaging. So now we're on to the question of scattering, of how this device performs outside of these sort of idealized environments. So the first thing that we did was to demonstrate this immunity to scattering in the collection system was to just introduce multiple layers of paraffin film between the object and the detector. And so we have a single frequency object here, and we looked at the fringe visibility of that single frequency object as a function of the depth of this scattering material. And so we can go over 100 scattering lengths without significant degradation of that fringe visibility, showing that collection system is relatively immune to scattering, so all we have to do is make sure that the illumination system can faithfully reproduce these modulation patterns. So we started looking at that in terms of how the depth of field of this system compares to a typical system. This is that same spatial frequency, single spatial frequency grading. And we propagated that away from the image plane. Oh, this is in millimeters here. And so the working distance of this objective is about 0.5 millimeter. But you can see that we get this re-imaging. We maintain this spatial frequency content over a huge amount of defocus. And the defocus in this case goes like the inverse of the numerical aperture, whereas for a focused beam, you would expect it to fall off as the inverse of the square of the numerical aperture. And so you can see we're able to penetrate quite deeply with some of these low spatial frequencies, although we do, as you can tell, start to lose some resolution as things blur out as we propagate further away from the plane. So we then introduced scattering to this measurement by putting this Raunchy ruling, the single frequency grading, into a scattering liquid. We just used a little bucket of milk and measured how far into the milk we could translate this sample and what the fringe visibility, or what in this case the harmonic weight, looks like. So this is our fundamental harmonic, and then because we're using binary modulation, we have a third, a fifth, a seventh, and so on and so forth. And so if we pulled out lineouts of the visibility of the first, third, and fifth harmonic, and so we can see the fifth harmonic down to about 500 microns into the 1% milk, so right about here. And then the fundamental and the third harmonic last a little bit longer. Now, this is some preliminary data, and so it looks like we're able to go quite deep relative to the frequencies that we're using, and this is sort of an active area that we're exploring in order to improve this technique and really understand how this works under scattering conditions. And so we'll wrap up a little bit. We've demonstrated sort of the XY imaging metric and the XZ, and so the next thing to do is to marry all of those together. We want to be able to expand the field of view on that. We want to be able to increase the axial sectioning by using Two-Photon or using some other sort of nonlinear processes in order to introduce real sectioning without having to do the tomography. And then we really are interested in looking at and optimizing the robustness to this scattering. And so this work was done in collaboration with several people in our group, Dr. Jeff Field, our current postdoc, and then Keith Wernsing, Philip Schultz, and Dan Higley were big into this work. And a lot of the biological side of things was actually done by some of our collaborators in the School of Biomedical Engineering, Stu Tobit and Shane Henches. And then we had this ongoing collaboration for some of the nonlinear work with Dr. Squire at Colorado School of Mines. So got a bit off track there and finished up a bit early, but I can take any questions that you guys might have.